In the grand, silent theatre of the cosmos, our sun is but one of countless stars, a solitary point of light in an ocean of shimmering contemporaries. For millennia, humanity has looked up at this celestial tapestry, dreaming of worlds beyond our own, of shores untouched by human feet. We charted the constellations, named the wandering stars we call planets, and slowly, meticulously, pieced together the architecture of our solar system. We felt, for a brief, triumphant moment, that we had mapped our local waters, but the true ocean, vast and deep, lay beyond. It was an expanse so profound that its distances could not be measured in the familiar miles or kilometers of our terrestrial experience, but only in the relentless march of light itself. 4.25 years, traveling at the universe's ultimate speed limit. That is the gulf that separates us from our nearest stellar neighbor, a dim, unassuming red dwarf star named Proxima Centauri. For most of astronomical history, it was a footnote, the faint companion to the brighter, more glamorous binary pair of Alpha Centauri A and B. It is a star so feeble that despite its proximity, it is utterly invisible to the naked eye, a cosmic ember glowing faintly in the constellation of Centaurus. It is a flare star, prone to violent, unpredictable outbursts of radiation, a tempestuous and volatile furnace. It seemed an unlikely place to begin our search for another Earth, and yet, in the year 2016, a whisper became a roar. After years of painstakingly analyzing the most subtle gravitational wobbles of this diminutive star, astronomers announced a discovery that electrified the world. They had found a planet. A world designated Proxima B, orbiting directly within its star's habitable zone, that delicate, temperate ribbon of space, where liquid water could potentially exist on a planet's surface. It was a revelation of staggering importance. The closest possible exoplanet to our own solar system was not a sterile gas giant or a scorched rock, but a world with at least the potential for life. The dream of interstellar travel, long the domain of fiction, suddenly had a destination. A tangible, tantalizing, real place. A new world just next door. The journey, it seemed, was finally upon us. The great human diaspora into the cosmos was about to begin. But this initial surge of intoxicating optimism soon collided with a wall of brutal, unforgiving physics. The journey to Proxima B is not merely difficult, it is a quest that pushes against the very limits of what is possible. It is a voyage that challenges our technology, our biology, our psychology, and our very conception of time. It is, by every measure we currently possess, the impossible journey. The chasm between us and that world is not just one of space, but of imagination. To truly comprehend the scale of this undertaking, we must first abandon our earthly intuition for distance. Let us construct an analogy. Imagine our entire, magnificent solar system, from the blazing surface of the Sun to the distant, icy orbit of Neptune, is shrunk down until it fits perfectly onto the surface of a small coin, a United States quarter. On this scale, Earth is a microscopic dust mote, invisible to the naked eye. Our fastest spacecraft, the Parker Solar Probe, which whips around the Sun at over 400,000 miles per hour, would on this coin-sized scale move at a pace slower than a crawling snail. Now, with this tiny, coin-sized solar system in the palm of your hand, where is Proxima B? Is it across the room? Is it in the next building? No. On this scale, the destination, the quarter representing Proxima Centauri's system, is over 4 football fields away. The fastest object ever launched by humanity is that very Parker Solar Probe. If we were to aim its incredible velocity directly at Proxima B, a straight shot into the interstellar dark, the journey would take approximately 6,600 years. Consider that. The entirety of recorded human history, the rise and fall of the Egyptian, Greek, and Roman empires, the Dark Ages, the Renaissance, the Industrial Revolution, the dawn of the digital age, all of this would unfold more than once over the course of that single voyage. Our messenger would arrive at its destination to find a world that might be inhabited by creatures who could be descendants of a civilization that had long since forgotten its terrestrial origins. The Voyager 1 probe, our farthest flung emissary, has been travelling for nearly half a century and has only just breached the Sun's magnetic influence. It would require 75,000 years to cross the void to Proxima Centauri. 75 millennia. A timescale not of history, but of geology, of evolution. The fundamental barrier is the tyranny of the rocket equation, a stark principle first formulated by the brilliant Russian visionary Konstantin Tsiolkovsky at the dawn of the 20th century. The equation dictates that to achieve a higher final velocity, a rocket must carry exponentially more fuel, but that fuel has mass, which requires even more fuel to accelerate it, which in turn adds more mass. It is a vicious, recursive cycle. Our majestic chemical rockets, the behemoths that carried us to the moon, are magnificent machines, but they are fundamentally inefficient. They are like trying to cross an ocean in a vessel that must carry every drop of fuel for the entire journey from the moment it leaves the harbour. For an interstellar voyage, the required fuel would be more massive than entire mountains, the resulting spacecraft impossibly vast. Chemical rockets have conquered our solar system, but they will never, ever breach the interstellar abyss. The physics is simply and cruelly against them. So, the dream seems to die before it even begins, dashed against the unforgiving mathematics of propulsion and the sheer, soul-crushing vastness of space. But even if we could somehow conjure a vessel capable of making the journey, what kind of world would we find at the end of it? Our initial, romantic visions of a verdant, blue-green paradise, a second Earth, have been steadily eroded by the harsh realities of Proxima Centauri's nature. This is not a gentle, life-giving star like our own Sunday. It is a red dwarf, a star type known for its violent temper. Proxima Centauri is a flare star, meaning it is prone to sudden, cataclysmic eruptions of energy. Imagine a stellar flare, a magnetic storm on the surface of the star that is hundreds, even thousands of times more powerful than anything our own sun has ever produced. These outbursts would blast Proxima B with a torrent of high-energy X-rays and charged particles. Any nascent atmosphere would be systematically stripped away, eroded over millions of years like a coastline battered by a relentless hurricane. The surface of the planet would be periodically scoured and sterilized by radiation levels that would be instantly lethal to any known terrestrial life form. Our dreams of walking on alien soil beneath a crimson sun must first contend with the reality of a world under constant, high-energy siege. Furthermore, the planet's close proximity to its small star means it is almost certainly tidally locked. Just as the moon always presents the same face to the Earth, Proxima B would be frozen in its orbital dance, one hemisphere perpetually baked in the star's unblinking gaze, the other locked in an eternity of absolute zero darkness and cold. The day side would be a scorched, desiccated desert, its water long ago boiled away into space. The night side would be an unimaginably frigid wasteland, its atmosphere frozen solid, forming glaciers of nitrogen and carbon dioxide on a surface that has not felt the warmth of its star for billions of years. This is not a cradle for life as we know it. It is a world of savage extremes, but even in this desolate picture, hope finds a sliver of land to cling to. Between the inferno of the dayside and the cryo-hell of the nightside lies a region of perpetual twilight. This is the Terminator Zone, a thin, circumnavigating band where the red dwarf star would hang eternally on the horizon, never rising, never setting. Here, in this realm of endless dawn or dusk, temperatures might be moderate enough for liquid water to flow. It is here, in the dim, ruddy twilight, that the search for life would concentrate. Life, if it exists on Proxima B, would be unlike anything we could imagine. It would have evolved under a sky dominated by a blood-red, motionless sun. Photosynthetic organisms might use pigments tuned to the lower energy infrared light of the red dwarf, painting the landscape in shades of black and deep purple. Creatures would have to be incredibly resilient, perhaps living underground or in deep oceans to shield themselves from the star's frequent, murderous flares. They would have to withstand the ferocious winds that would ceaselessly howl from the hot hemisphere to the cold one, a planet-spanning atmospheric engine driven by the extreme temperature gradient. Life on Proxima B would be a testament to tenacity, a form of existence forged in radiation and tempered in twilight. The journey remains impossible, and the destination has become profoundly alien. Faced with these insurmountable obstacles, the human spirit does not surrender, it innovates. If conventional rockets are insufficient, we must dream of unconventional engines. We must design machines born not of chemistry, but of the fundamental forces of the universe itself. In the mid-20th century, during the feverish height of the Cold War and the atomic age, some of the most audacious minds conceived of a craft that would ride to the stars on a wave of nuclear explosions. It was called Project Orion. The concept was as brutal as it was brilliant. A massive spacecraft with a thick, armored pusher plate at its rear. From the ship, small, directional atomic bombs would be ejected and detonated, one after another, in rapid succession. Each blast would vaporize a propellant disk, creating a plasma wave that would strike the pusher plate, driving the colossal vessel forward. It was a vision of controlled, sustained nuclear violence, a starship that pulsed its way across the cosmos. Calculations showed it was surprisingly feasible. An Orion-class vessel could reach Proxima Centauri in just over a century, a vast improvement over millennia, and a time frame perhaps manageable for a multi-generational mission. But the project was a child of its time. The signing of the Partial Test Ban Treaty in 1963, which prohibited nuclear explosions in the atmosphere and in space, effectively ended the dream of Orion. The thought of launching a ship laden with thousands of nuclear warheads from Earth was, and remains, a political and environmental impossibility. A more elegant, though no less ambitious, concept emerged from the British Interplanetary Society in the 1970s. Project Daedalus was a design for an unmanned probe propelled by nuclear fusion, the same process that powers the stars themselves. The Daedalus vessel would be an enormous, two-stage craft, assembled in orbit, its mass composed almost entirely of fuel. It would carry pellets of deuterium and helium-3, isotopes that would be injected into a reaction chamber and ignited by powerful electron beams, creating miniature thermonuclear explosions. These contained detonations would generate a superheated plasma exhaust, propelling the probe to an astonishing 12% of the speed of light. The journey to Proxima Centauri would be reduced to a mere 50 years, a single human lifetime. The engineering challenges, however, were gargantuan. We have yet to achieve sustainable, energy-positive fusion power on Earth, let alone miniaturize it into a reliable spacecraft engine. The fuel, helium-3, is exceedingly rare on our planet and would need to be mined from the atmosphere of a gas giant, like Jupiter, a colossal undertaking in itself. Daedalus was a magnificent blueprint, a testament to human ingenuity, but it required a level of technology and infrastructure that remains decades, if not centuries, beyond our grasp. It was a theoretical solution to an impossible problem. Perhaps, then, the answer is not to carry the fuel with us at all. Perhaps the secret is to travel light, to build a craft that can ride upon a wind that blows between the stars. This is the principle behind the solar sail. Just as a sailboat uses the pressure of wind against its canvas, a solar sail uses the pressure of photons, particles of light streaming from a star. This pressure is incredibly faint, but in the frictionless vacuum of space, its gentle, continuous push can build up immense velocity over time. A vast, gossamer-thin sail, kilometers wide but no thicker than plastic wrap, could be unfurled in orbit and slowly, gracefully, accelerate on the river of sunlight flowing from our star. But the sun's light, while powerful, weakens dramatically with distance. To achieve the truly relativistic speeds needed for an interstellar journey, a much more powerful light source is required. This is the core idea behind Breakthrough Starshot, a visionary project announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner. The concept is breathtaking in its scale and ambition. The Starship would not be a massive vessel, but a tiny, gram-scale microchip, the Starchip, packed with cameras, sensors, and a communications laser. This chip would be attached to a sail, the light sail, just a few meters across. The propulsion system would not be on the craft. It would remain here, on Earth. It would be a colossal, ground-based laser array, miles in diameter, composed of millions of individual lasers, all firing in perfect unison. This system would generate a beam of light with 100 gigawatts of power, more than the entire output of many countries, and focus it with pinpoint accuracy on the tiny sail floating in orbit. For a few minutes, this titanic beam of pure energy would accelerate the starship to 20% of the speed of light. At that velocity, the journey to Proxima B would take just over 20 years. The probe would whip through the Proxima Centauri system in a matter of hours, frantically capturing data and images, which it would then beam back to Earth using its tiny onboard laser. The light from that transmission, carrying the first close-up images of another world, would itself take 4.25 years to reach us. The challenges are monumental. How do we build and power such a laser? How do we keep the beam focused on a meter-wide sail millions of miles away? How does the fragile chip survive the journey through interstellar dust, where even a single grain impact at that speed would be catastrophic? Starshot pushes technology to its absolute breaking point, but it represents the first truly plausible roadmap for sending a robotic emissary to another star within our lifetimes. Yet, even these revolutionary concepts pale in comparison to the ultimate form of propulsion, a power source drawn from the very fabric of reality, antimatter. When a particle of matter meets its corresponding antiparticle, they annihilate each other in a perfect conversion of mass into pure energy, as described by Einstein's famous equation, E equals mc squared. It is 100% efficient, the most potent and energy-dense fuel theoretically possible. A spacecraft powered by matter-antimatter annihilation could reach Proxima Centauri in a matter of years, not decades, potentially even carrying a human crew. The problem is that antimatter is the rarest and most expensive substance in the universe. We can create it in infinitesimally small quantities in particle accelerators like the ones at CERN, but the process is stupendously inefficient. To produce a single gram of antimatter enough to power a significant mission would require all of humanity's current energy output for centuries, and would cost a sum so astronomical it is meaningless. Quadrillions upon quadrillions of dollars. And even if we could produce it, storing it is another Herculean task. Antimatter must be contained in a perfect vacuum, suspended by powerful magnetic fields, because the slightest contact with normal matter would result in a catastrophic explosion. The engineering required for a reliable antimatter engine makes fusion reactors look like child's play. It remains a technology of the far, far future. The sheer difficulty of achieving these incredible speeds forces us to consider a slower, more patient path. If we cannot shrink the journey's duration, perhaps we must instead expand the human lifespan to fit the journey. This leads to one of science fiction's most enduring and haunting concepts, the generation ship. A colossal vessel, a self-contained world in miniature, carrying an entire community of people. This ark would not be a means of transport for its original crew, but a home. They would live out their lives aboard the ship, and their children, and their children's children, would inherit the voyage. Generations would be born, live, and die within its metallic confines, knowing only the artificial sky of the ship's interior and the unchanging starfield outside. The final destination would be a promised land for their distant descendants, a myth whispered down through the ages. Creating such a world is an ecological challenge of unimaginable complexity. The ship would need a perfectly closed-loop life support system, a miniature biosphere that could flawlessly recycle every atom of air, water, and waste for centuries. We have attempted such experiments on Earth, like the Biosphere 2 project, and they have met with limited success over a period of just 2 years. A generation ship would have no room for error. A single, unaddressed failure in the ecosystem, a crop blight, a microbial imbalance, a broken water purifier, could doom the entire mission hundreds of light years from any possible help. The psychological and sociological burdens would be even more immense. What would become of a society confined for a dozen generations? How would their culture evolve, their language shift, their purpose remain intact? Would the descendants, born into a world of metal and recycled air, still feel a connection to the distant, legendary planet of their ancestors? Or would they see themselves as a separate people, the shipborne, with no allegiance to the ghosts of Earth? They would be the most isolated tribe in human history, adrift in an existential solitude that we can barely comprehend. The mission's greatest threat might not be a meteor or a mechanical failure, but the simple, corrosive effects of time on the human spirit. There is another, perhaps more direct, alternative to the generation ship: suspended animation. The idea of placing a human crew into a state of deep hibernation or cryosleep, pausing their biological processes for the long, empty centuries of the voyage, only to be reawakened upon arrival. Nature provides tantalizing clues. Bears hibernate, lowering their metabolism for months. Certain species of frogs and fish can survive being frozen solid, their cells protected by natural cryoprotectants. But the leap from a hibernating bear to a frozen human is a chasm of biological complexity. The primary danger is ice crystal formation. When water freezes, it expands and forms sharp, jagged crystals that would pierce and shred delicate cell membranes, causing irreparable damage on a massive scale. Vitrification, a process of flash freezing that turns cellular fluid into a glass-like solid without crystal formation, offers a potential solution, but it is an experimental science in its infancy. We do not know how to safely induce such a state in a complex organism like a human, let alone how to reverse it decades or centuries later without causing catastrophic neurological or systemic damage. The dream of a long sleep between the stars remains, for now, firmly in the realm of fiction. The silent voyagers of our imagination have not yet found a way to cheat time's unforgiving arrow. Let us imagine, for a moment, that we overcome all of these things. We build the impossible engine, we solve the problem of human longevity, and we launch our magnificent starship. The crew, whether they are the distant descendants of the original voyagers or resurrected sleepers from a bygone era, finally approach their destination. After a journey that has consumed centuries of human endeavor, the dim red spark of Proxima Centauri grows in the forward viewports, resolving into a small, angry, crimson star. And there, a tiny speck against its glare, is the prize, Proxima B. The first readings would be a torrent of information, a scientific treasure trove beyond compare. The probe would analyze the planet's atmosphere, searching for the telltale biosignatures of life: oxygen, methane, water vapor. It would map the surface, revealing the geography of the Terminator Zone, seeking the glint of liquid oceans or the contours of alien continents. For the first time, the abstract data point from 2016 would become a real place, a world with weather, geology, and history. The first images would be transmitted back across the 4.24 light-year gulf, each pixel a testament to the greatest journey ever undertaken. We would see a landscape painted in hues utterly alien to us. Under the perpetual, dim red light, the sky might appear a deep, brooding violet. If plants exist, they might be black, evolved to absorb as much of the faint star's energy as possible. We might see vast, wind-scoured plains where the atmosphere howls from the hot side to the cold. We might discover deep, shielded canyons where life has taken refuge from the star's radiation. Or perhaps we will find a global ocean, its surface churned by thermal tides, its depths concealing an ecosystem that has never known the light of its own sun. The ultimate discovery, of course, would be life itself. Even a single, unambiguous, alien microbe found in a sample of soil or water would be the most profound discovery in the history of science. It would answer the ancient, lonely question: are we alone? The existence of a second, independent genesis of life would imply that life is not a fluke, not a miracle unique to Earth, but a common, perhaps inevitable, outcome of cosmic chemistry. It would mean the universe is teeming with biology, and we are just one small, newly aware part of a vast, living cosmos. The philosophical and cultural impact of such a discovery would be transformative, reshaping our understanding of our place in the universe forever. But we must also be prepared for the alternative. The instruments may report back that the atmosphere is sterile, stripped bare by the star's flares. The surface may be a radioactive wasteland, utterly devoid of the complex chemistry needed for life. The terminator zone might be nothing more than a lifeless band of fractured rock. Proxima B could simply be a dead world. The silence from that distant planet would be a discovery of a different kind, a quiet, sobering confirmation of the preciousness and rarity of our own living world. It would underscore the staggering good fortune of our existence on this fragile blue oasis, a sanctuary in a universe that appears, for the most part, to be actively hostile to life. And so, we are left with the paradox of Proxima B. It is the closest destination, yet it is impossibly far. It is a potential haven, yet it is a confirmed hellscape. It is the object of our greatest ambition and the symbol of our profoundest limitations. The journey itself, the very act of striving to reach it, may be more important than the destination. The technologies we must invent to even attempt such a voyage, fusion power, advanced materials, closed-loop ecosystems, artificial intelligence are the very technologies that could solve many of the most pressing problems we face here on Earth. The quest for the stars could be the very thing that saves our world. Perhaps, in the end, the impossible journey is not a physical one made by a ship, but a conceptual one made by a species. It is a journey of knowledge, of pushing our understanding of physics and biology to their absolute limits. It is a journey of perspective, of recognizing the immense, cosmic scale of our existence and the incredible fragility of our home. We may never stand on the twilight plains of Proxima B. We may never watch its red sun hang motionless in a purple sky. But by dreaming of it, by designing the vessels to take us there, by aiming our minds and our hearts at that distant point of light, we are already undertaking the voyage. We are already becoming a species of the stars. The destination is not a planet, but a future, and the journey, impossible as it seems, has already begun. Every second of your existence, you're hurtling through the cosmos at over 1 million miles per hour. This is not the gentle, familiar spin of the Earth, nor its stately waltz around the sun. This is a different kind of motion, a grand, directed and relentless pilgrimage across the unimaginable emptiness between the galaxies. You're not wandering aimlessly through the void. You're being summoned by a force of such incomprehensible scale that it reaches across millions of light years to take hold of our entire galaxy and everything within it. It is an invisible tether, a gravitational summons from an unseen source drawing the Milky Way and all its neighbours into a cosmic current, a river of star systems flowing towards a destination we're only just beginning to comprehend. This journey is not a choice. It is our destiny written into the very fabric of space-time by the uneven distribution of mass left over from the dawn of creation. For eons, our ancestors looked to the heavens and saw fixed points of light, a static and eternal celestial sphere. They charted constellations seeking meaning in the patterns, never dreaming that the entire canvas was in motion, that our home was a tiny vessel caught in a titanic gravitational tide. But now we know. We have measured the subtle shifts in the ancient light from the Big Bang, the cosmic microwave background, and we have discovered our velocity. We have mapped the galaxies around us, triangulating our trajectory, and we have identified the source of this inexorable pull. It is not a single object, not a monstrous black hole or a rogue supergalaxy, but something far more vast and complex. It is a city of light, a sprawling luminous metropolis of galaxies, a celestial hub whose collective gravity dictates the flow of cosmic traffic for 100 million light years in every direction. This gravitational anchor, this magnificent congregation of matter, is the Virgo cluster, and we are falling towards it. To truly grasp the significance of this place, to understand why it holds the key to our cosmic past and our ultimate future, we must first undertake this journey ourselves. We must leave behind the familiar comforts of our homeworld and venture out following the same path our galaxy is destined to travel. Our voyage begins here on a small blue marble, a fragile oasis of a life suspended in the silent expanse. From this vantage point, the universe appears serene, a quiet and orderly place. But as we pull away, leaving Earth's gentle atmosphere behind, the true scale of our surroundings begins to assert itself. The moon, a loyal companion and a stepping stone to the stars, recedes into a pearlescent dot. The planets of our solar system, worlds of fire and ice, become mere specks of wandering light, their intricate orbits now just faint loops around a single, unremarkable star. We push outward past the Kuiper Belt's icy debris, and through the Oort cloud, a ghostly spherical shell of dormant comets marking the outermost boundary of our Sun's gravitational kingdom. Here a profound loneliness sets in. The Sun, the source of all our warmth and life, has shrunk to become the brightest star in a sea of countless others. And then we take the ultimate leap. We cross the threshold into interstellar space, leaving our solar system entirely behind. From this new perspective, our home galaxy, the Milky Way, reveals itself in its full breathtaking splendor. It is a colossal spinning disk of 100 billion stars, a luminous spiral vortex of gas and dust. We see the majestic arms glittering with the blue-white fire of newborn suns curving gracefully out from a brilliant golden core, where an ancient supermassive black hole slumbers. This is our home, our island universe, a structure so vast that a beam of light would take 100,000 years to cross it. And yet from out here we can see with shocking clarity that it is just that, an island adrift in an ocean of staggering emptiness. Looking around, we find we are not entirely alone. The Milky Way belongs to a small gravitationally bound collection of about 50 galaxies known as the Local Group. It is a quiet cosmic neighbourhood. Our nearest major rival and future partner in a cataclysmic merger is the Andromeda Galaxy, another majestic spiral even larger than our own, hanging in the darkness just 2.5 million light-years away. Dotted around these two titans are smaller dwarf galaxies like the Magellanic Clouds, obediently orbiting the Milky Way like celestial moons. For a moment, this seems to be the extent of our universe, this cosy archipelago of star systems. But this is merely the suburb. Our journey's true destination lies much farther ahead, across a chasm of intergalactic space so profound it challenges the imagination. We set our course towards the constellation Virgo, following the gravitational current that pulls at our very existence. The void we must now cross is almost absolute. For millions of years, at the speed of a light, we would travel through a darkness punctuated only by the faint ghostly light of the most distant galaxies. Space here is emptier than the most perfect vacuum we can create on Earth. The silence is total. The cold is near absolute zero. It is a realm where the density of matter drops to just a few atoms per cubic meter, a cosmic desert that seems to stretch on into infinity. During this long transit, the Local Group shrinks behind us, its familiar spirals and glowing halos dissolving back into the general tapestry of the cosmos, becoming indistinguishable from any other faint smudge of light. Then, after traversing more than 50 million light-years of this stark wilderness, something begins to change. The darkness begins to feel less absolute. The emptiness feels less empty. At first, it is subtle, a statistically improbable clustering of faint pinpricks in a single patch of sky. Then these pinpricks resolve into distinct shapes, spirals seen to edge on like cosmic razors, fuzzy glowing ovals, irregular splotches of light. They are galaxies, not one or two but dozens, then hundreds. Suddenly, we're no longer in the empty wilderness, but have reached the outlying districts of a truly vast cosmic settlement. We have arrived at the Virgo cluster. The view is overwhelming, a scene of celestial grandeur on a scale that dwarfs everything we have witnessed before. Stretching across 10 million light-years of space, this is not a neatly organized group like our own, but a dynamic, sprawling and chaotic megalopolis of over 2,000 galaxies. It is the gravitational and energetic heart of our corner of the universe, a place of constant creation and relentless destruction. If our Local Group is a quiet village, Virgo is a bustling, cacophonous and dazzling capital city. Navigating into its heart is like flying through a three-dimensional tapestry of light. Everywhere you look, there are galaxies of every conceivable shape, size, and colour. Graceful blue-tinted spirals, much like our Milky Way, drift through the cluster's periphery. These are the newcomers, recent arrivals still rich with the gas and dust needed to form brilliant new stars. Their spiral arms are illuminated by the fierce ultraviolet glare of stellar nurseries churning out suns by the millions. They are vibrant, active, and alive. But their beauty is fragile, their fate precarious. They are like small ships being drawn into a powerful maelstrom from which there is no escape. As we press deeper towards the cluster's core, the environment changes dramatically. The space between the galaxies is no longer empty. It is filled with a ghostly, searingly hot gas, an intracluster medium heated to millions of degrees detectable only by our X-ray telescopes. This is the cluster's atmosphere, a phantom fog woven from the gas violently stripped from countless galaxies that have passed this way before. It is a cosmic graveyard containing more mass than all the stars in all the cluster's galaxies combined. And within this superheated haze, we see the galactic population transform. The elegant spirals become fewer and farther between. In their place, we find distorted, misshapen galaxies, their arms torn and frayed, trailing long streamers of gas and stars behind them like cosmic contrails. These are galaxies in the throes of a violent transformation, being battered and scoured by the hostile environment of the cluster's interior. Then, at the very centre of this celestial storm, we find the rulers of this realm, the giant elliptical galaxies. These are not spiral galaxies. They are colossal, featureless, incandescent spheres of ancient stars, the largest and most massive galaxies in the known universe. They glow with the soft reddish-yellow light of old dying suns containing trillions of stars packed into a dense gravitational core. At the heart of the Virgo cluster sits the undisputed monarch Messier 87 or M87. It is a behemoth, a cosmic monster, that has grown to its current size by relentlessly consuming its smaller neighbours over billions of years. M87 is a galactic cannibal. We can see the faint, ghostly shells of its past victims, the tidally shredded remains of entire galaxies now orbiting its core like phantoms, and deep within its centre, hiding behind a veil of 1 trillion suns, lies one of the most powerful engines in the cosmos, a supermassive black hole weighing 6.5 billion times more than our Sun. This is the black hole we have famously imaged, a ring of fire surrounding a point of infinite darkness. From its poles it ejects a colossal jet of high-energy particles that travels for thousands of light years, a celestial blowtorch slicing through the cluster's atmosphere. M87 and other giant ellipticals like Messier 84 and Messier 86 that dominate the cluster's core represent the end state of galactic evolution. They are the quiet, satiated predators in a cosmic ecosystem, having long ago exhausted their fuel for making new stars. They are in a sense red and dead. This incredible, diverse and violent spectacle is far more than just a beautiful sight. The Virgo cluster is our most important cosmic laboratory. It is a unique environment where we can witness the fundamental forces that shape the universe playing out on the grandest possible scale, providing crucial answers to our most profound questions. For astronomers, Virgo is a time machine. By studying the different populations of galaxies within it, from the young star-forming spirals on the outskirts to the ancient quiescent ellipticals at the core, we can piece together the complete life story of a galaxy. We can see what the Milky Way might have looked like in its youth, and we can witness the fate that awaits it if it strays into such a crowded and dangerous environment. Here we see the brutal mechanisms of galactic transformation in action. We witness a process called RAM pressure stripping, where a galaxy moving at high speed through the hot intracluster gas has its own interstellar gas scoured out of it, like a fierce wind extinguishing a candle flame. This process prematurely halts star formation, effectively killing the galaxy and transforming a vibrant spiral into a gas-poor anemic system. We also see the devastating effects of tidal stripping, where the immense gravity of a larger galaxy tears a smaller one apart, unravelling its spiral arms and siphoning its stars into long faint streams. And of course we see galactic cannibalism, the final act, where one galaxy completely swallows another in a chaotic merger that reshapes both. The Virgo cluster, therefore, is not just a collection of objects, it is a dynamic process, a grand celestial experiment showing us how the universe builds its largest structures and how galaxies like living organisms are born, evolve, and eventually die. But the secrets held within this magnificent cluster go even deeper, pointing to an even greater mystery that permeates the entire cosmos. When we measure the velocities of the galaxies within Virgo, we find something deeply unsettling. They are moving at astonishing speeds, far too fast to be held in orbit by the gravity of the matter we can see. Based on the combined mass of all the stars, gas and dust within the cluster, Virgo should have flown apart billions of years ago. The galaxies should have scattered into the void like shrapnel from an explosion, and yet they remain bound together. There must be an enormous amount of extra mass present, a powerful gravitational glue holding this entire metropolis together. It is a mass that we cannot see, that does not shine, reflect, or interact with light in any way. This is the overwhelming evidence for dark matter. The Virgo cluster acts as a cosmic scale, allowing us to weigh the unseen. By observing how the cluster's immense gravity bends and distorts the light from more distant galaxies behind it, a phenomenon known as gravitational lensing, we can create a map of all the mass that is present. This map reveals a staggering truth. The luminous galaxies, the shining stars, the glowing gas, all the matter that we are familiar with, accounts for less than 15% of the cluster's total mass. The other 85% is this mysterious invisible substance. The beautiful galaxies we see are merely the bright foam on a vast unseen ocean of dark matter. This ghostly architect forms the true scaffolding of the cluster, an enormous invisible halo within which the visible galaxies are embedded like luminous jewels. Studying Virgo gives us one of our clearest views of the distribution and influence of this enigmatic component of our universe, a substance that dictates the structure of the cosmos on the largest scales yet, whose fundamental nature remains one of the greatest unsolved puzzles in all of science. And this brings us back to our own story, back to that inexorable pull we feel across 54 million light-years of space. The immense gravitational field of the Virgo cluster, amplified by its colossal dark matter halo, is the engine driving our cosmic journey. It is the heart of the Laniakea supercluster, a titanic structure of 100,000 galaxies, of which our local group is just a tiny outlying component. Laniakea is not just a collection of galaxies, it is a watershed, a gravitational basin. And all the galaxies within it, like raindrops on a vast landscape, are flowing downhill towards the most massive concentration of matter in the region, the Virgo cluster. This motion is called the Virgo infall. We, along with Andromeda and all our small satellite galaxies, are part of this great migration. We are currently on the far edge of Laniakea's basin, just beginning our long descent. Our fate, billions of years from now, is to fall into this crowded, violent and magnificent city of galaxies, to be consumed by its gravitational influence and to be transformed by its hostile environment. The Virgo cluster, therefore, is not some distant, disconnected astronomical curiosity. It is our cosmic anchor. It is a laboratory for understanding the birth and death of galaxies. It is a crucible for testing our theories of dark matter and gravity. And it is ultimately a preview of our own distant destiny. To understand our place in the cosmos, to unravel the unseen forces that shape reality, and to glimpse the final chapter of our own galactic story, we must first journey into the heart of this magnificent, violent and beautiful storm of stars. We must enter the Virgo cluster. Before we could ever hope to understand our place in the cosmos, we first had to conquer a more fundamental human challenge, the tyranny of perspective. For millennia, our universe was a comfortable, familiar room. Its ceiling was a velvet tapestry of stars, its walls the luminous Milky Band of our own galaxy. Everything we saw, we believed, was contained within this single magnificent home. Yet scattered across that celestial wallpaper were faint, ghostly smudges of light, ethereal whirls and soft ellipses that defied easy explanation. To the astronomers of the early 20th century, these were the ultimate enigma, the spiral nebulae. What were they? Were they nascent solar systems swirling into being within our own cosmic backyard? Or perhaps they were strange celestial weather patterns, storms of gas and dust, raging in the distant reaches of the Milky Way? The debate raged with an intellectual ferocity that defined an entire era of science. On one side stood the formidable Harlow Shapley, a man who had measured the vastness of our own galaxy and concluded it was in effect the entire universe. To him, these nebulae were local phenomena subordinate pieces of the one great stellar empire he had charted. On the other side was Heber Curtis, who championed a far more radical, almost philosophically unsettling idea. He argued that these smudges were not internal affairs at all. They were, he proposed, island universes, entire galaxies just like our own lying at distances so immense they beggared the human imagination. It was a cosmic schism, a debate that pitted the comfortable and known against the terrifyingly vast and unknown. The very scale of reality hung in the balance, waiting for a final, irrefutable verdict. To settle it, humanity needed not just better theories but better eyes capable of peering deeper into the void than ever before. Long before this grand debate reached its fever pitch, however, the groundwork for discovery was being laid not by a philosopher seeking to map the cosmos, but by a frustrated Frenchman hunting for comets. In the 18th century, Charles Messier spent his nights sweeping the Parisian sky, yearning for the glory of finding those icy wanderers that were the astronomical prizes of his day. But his work was constantly interrupted by deceptive impostors, faint fixed, fuzzy objects that mimicked the appearance of a distant comet, but stubbornly refused to move. Annoyed, he began to compile a catalogue of celestial nuisances to be ignored in his primary quest. He had no grander ambition for it. It was a practical tool, a do not disturb sign hung upon the doors of a deep space. And yet, in one of the most beautiful ironies in the history of science, Messier's list of frustrations would become our first true roadmap to the grandest structures in existence. His catalogue of about 100 objects was a treasure chest of cosmic wonders, and he had no idea he was holding the key. As he charted these annoyances, he must have noticed a peculiar pattern emerging from the star charts. While many of his nebulae were scattered across the sky, a remarkable number of them seemed to congregate in one specific direction within the borders of a single constellation, Virgo. Night after night, his telescope would drift through that patch of sky, and another faint smudge would appear in the eyepiece. First number 49, then 58, 59, 60. Then a great cluster of the Messier 84, 86, and the strangely bright featureless orb of Messier 87. Imagine what he saw through his primitive brass and glass telescope. Not the crisp, glittering portraits our modern instruments provide, but something far more ethereal and ghostly. Through the wavering atmosphere, he would have perceived them as silent, luminous breaths. Against the black, their forms maddeningly indistinct. He could not see their spiral arms or their billions of individual stars. To Messier, this region of the sky must have felt haunted, a celestial graveyard, or a nursery of cosmic ghosts, whose nature was utterly beyond his comprehension. He meticulously noted their positions, described their faint shapes, and moved on forever unaware that he was the first human cartographer of a galactic metropolis. He was in effect sketching the faint lights of a distant city from a hilltop, believing he was merely mapping a patch of local fog. This dense collection of nebulae in Virgo became known to later astronomers as the realm of the nebulae, a profound concentration of cosmic mystery that demanded an explanation far beyond the science of Messier's time. The answer, when it finally came, did not arrive as a gradual dawn of understanding, but as a singular thunderous crack that shattered the very firmament of our cosmic home. The stage for this revelation was the thin, clear air of Mount Wilson in California, and its protagonist was a quiet, meticulous astronomer named Edwin Hubble. Using the colossal 100-inch Hooker telescope, the most powerful eye on Earth, Hubble dedicated himself to solving the riddle of the spiral nebulae. He focused on the most famous of them all, the great Andromeda Nebula Messier 31. For long, cold nights, he captured its light on fragile glass photographic plates, building up an image of unprecedented depth and clarity. He wasn't just looking at the nebula, he was hunting within it, searching for a very specific kind of star. He was looking for a Cepheid variable, a rare type of star that pulses in brightness, with a rhythm directly linked to its true intrinsic luminosity. These stars are the universe's standard candles. If you can measure how fast one pulses, you know how bright it truly is. By comparing that true brightness to how dim it appears from Earth, you can calculate its distance with astonishing precision. And one fateful night in 1923, examining a plate from Andromeda, Hubble found one. He marked it on the plate with the letters VR for variable. In that single decisive moment of discovery, with a few lines of ink on a piece of glass, the universe fractured. The calculations were undeniable. The flickering star, and therefore the entire Andromeda Nebula containing it, was not thousands of light years away within our Milky Way. It was nearly 1 million light years distant, a staggering figure that placed it far, far outside the most generous boundaries of our own galaxy. The walls of our cosmic room did not just expand, they were utterly obliterated. Shapley was wrong, Curtis was right. The island universe theory was no longer a theory, it was a fact. Our Milky Way was not the universe, it was just one galaxy among countless, perhaps billions of others. This was an epiphany on par with Copernicus deposing the Earth from the centre of the solar system. Humanity was once again demoted, cast out from the centre, and adrift in an ocean of galaxies whose true scale was almost too vast for the mind to hold. And with this new terrifyingly expansive map of reality, astronomers turned their attention back to that strange, dense collection of smudges in the constellation Virgo. They were not local clouds of gas. They were not forming stars. They were galaxies, each and every one. Messier's realm of the nebulae was revealed to be something far more magnificent, the Virgo cluster. A colossal swarm, a city of starlight containing not dozens but thousands of entire galaxies, all bound together by their mutual gravity. Messier 87, that bright featureless orb, was not a simple nebula, but a monolithic giant and elliptical galaxy, containing perhaps trillions of stars dwarfing our own Milky Way into insignificance. The other Messier objects nearby, M84, M86, M90, were its neighbours' fellow titans in a gravitational dance on a scale never before conceived. The pioneering work of mapping these newly understood structures began in earnest, as astronomers used Hubble's methods to measure their distances and piece together the cluster's three-dimensional architecture. What they found was a structure of breathtaking proportions, a swarm of galaxies spanning millions of light years its core, a churning maelstrom of galactic collisions and gravitational tides. This was the birth of a new field of science, the study of large-scale structure. For the first time, we could see that galaxies were not scattered randomly through space like dust motes in a sunbeam. They were organised, they congregated, they formed families, groups, and massive clusters drawn together by the invisible, inescapable force of gravity. The universe, it turned out, had an architecture, a grand design, woven from filaments and walls of galaxies surrounding vast empty voids. The Virgo cluster was simply the nearest and most prominent example of this cosmic framework, the cornerstone of our local universe. But as astronomers refined their measurements of this galactic city, a new and even more profound mystery began to surface, one that implicated us directly. It wasn't just about what the cluster was, but what it was doing. They began by meticulously measuring the light from the galaxies in the cluster, analysing their spectra to determine their motion. Most were milling about the cluster's centre like bees around a hive, but the new mystery emerged when they turned their instruments away from Virgo and pointed them back toward our own cosmic neighbourhood, the small collection of galaxies we call the local group dominated by our Milky Way and Andromeda. We too are moving through space. The Earth orbits the Sun orbits the centre of the Milky Way, but the entire galaxy itself is also in motion, hurtling through the intergalactic void. And when astronomers carefully subtracted all of these local movements, they were left with a shocking residual velocity. A peculiar velocity, as they called it, that had no obvious explanation. The entire local group, our home, and everything in it is being pulled. We're falling. Our trajectory across hundreds of millions of years is not a random drift through the expanding universe. We're on a distinct path drawn by an unseen gravitational force toward a specific point in space. And when we trace that vector, that invisible tether that has us in its grip, it points directly toward the heart of the Virgo cluster. The immense city of galaxies that Messier first catalogued as a series of annoyances is our cosmic anchor. Its combined mass, trillions upon trillions of suns' worth, exerts a gravitational pull so profound that it reaches across more than 50 million light-years of empty space to grab hold of our galaxy and reel it in. We're not merely observing the Virgo cluster from a safe distance. We're active participants in its story, caught in its gravitational watershed, slowly but inexorably, being drawn toward its dense, chaotic core. The solution to one great mystery had in the most spectacular fashion given birth to another. We had finally understood the nature of the spiral nebulae, only to be confronted with the unnerving reality of our own motion. Why is this colossal superstructure here so relatively close to us? What cosmic process could assemble thousands of galaxies into such a dense and powerful collective? And what does its relentless gravitational pull mean for the ultimate fate of our own Milky Way? We had opened a door expecting to find a larger room, and instead found ourselves standing on the precipice of an infinite cosmic ocean, feeling the pull of a tide whose source was only just beginning to reveal its awesome power. The journey into the heart of Virgo was no longer just an astronomical curiosity, it had become a journey into understanding our own destiny. But that serene portrait, that silent, sprawling archipelago of light we first mapped from Earth was a profound and beautiful deception. It was a map drawn in the dark using only a single candle. To truly understand the Virgo cluster, to witness its furious incandescent heart, we had to become something more than human. We had to build new eyes for ourselves, eyes that could transcend the narrow sliver of reality our biology permits us to see. We had to leave the planet that birthed us, escaping the shimmering veil of our own atmosphere, to gain the clarity we so desperately sought. Our quest to truly chart this cosmic neighbourhood demanded a new generation of explorers, tireless, unblinking machines, sent to stand vigil in the cold vacuum of space. And so we did. We constructed our sentinels. Poised in orbit far above the distortions of air and weather, the Hubble Space Telescope became our species' transcendent eye. For decades it has pirouetted in the silent darkness, a magnificent gravitational gyroscope pointed at the universe's deepest secrets. It does not merely see light, it collects time itself. Each photon that strikes its polished mirror has travelled for 60 million years, a ghost of an event that unfolded when giant mammals still roamed our own world. Hubble's gaze is therefore a form of temporal archaeology. When we point it toward Virgo, we are not just looking across space, we are peeling back 60 million years of cosmic history to see the cluster as it was not as it is. The images it sent back shattered our quiet map forever. The elegant pinwheeling spirals and calm glowing ellipses we once saw as isolated islands were revealed to be actors in a violent ongoing drama. Here, captured in Hubble's unblinking stare, was the evidence of raw gravitational savagery. We saw galaxies that were not pristine but horrifically scarred. Great luminous streamers of stars, thousands of light years long, were being torn from spiral arms, flung out into the void like celestial blood spatter. These are the tidal tales, the ghostly remnants of a close encounter, a galactic sideswipe where the gravity of a larger neighbour has ripped its victim's starry flesh. In other corners of the cluster, we witnessed the aftermath of direct collisions. Two galaxies, their bright cores merging in a chaotic gravitational waltz, their gas clouds crashing together to ignite a furious wave of starbirth, a starburst that blazes with the light of millions of newborn blue-white suns. Hubble showed us that the Virgo cluster is not a tranquil city of stars. It is a sprawling, ruthless metropolis, a cosmic demolition derby on the grandest scale imaginable. Every portrait it captures tells a story of survival, of transformation, or of utter annihilation. We see majestic spiral galaxies, their delicate arms warped and twisted by the incessant gravitational tugging of their neighbours. We see enormous bloated elliptical galaxies like Messier 87, gorged on the stellar corpses of countless smaller galaxies they have consumed over billions of years. Hubble's vision allowed us to count the faint glimmering globular clusters surrounding these giant ancient relics that act as a fossil record of these cannibalistic feasts. The serene order we once imagined was replaced by a panorama of breathtaking, beautiful violence. Yet for all its power, Hubble's vision is fundamentally like our own. It sees the stars, the bright and shining structures that punctuate the darkness. It sees the consequences of the battle, but not the battlefield itself. It showed us the wounds, but it couldn't see the weapon. To perceive the true nature of the cluster's environment, to understand the invisible forces shaping these galaxies, we needed a different kind of sight. We needed to see the universe not in the gentle light of a star, but in the ferocious glare of the inferno. we needed X-ray vision. Enter the Chandra X-ray Observatory, our eye for the hot and violent universe. Flying even higher than Hubble, its uniquely shaped mirrors are designed to corral and focus high-energy photons, light so energetic it would pass straight through a conventional telescope. Chandra sees the universe of million-degree gas of shockwaves from supernova explosions and the maelstrom of matter spiraling into black holes. When we turned its gaze upon the Virgo cluster, we were expecting to see pinpoint sources of X-rays from black holes and neutron stars. We saw those, yes. But we also saw something else, something vast, ethereal, and utterly unexpected that permeated the entire cluster. It was a ghost, a colossal luminous shroud of superheated gas, a phantom atmosphere binding all the galaxies together. This is the intracluster medium, the ICM. It is an immense ocean of plasma heated to tens of millions of degrees, glowing faintly but powerfully in X-ray light, and it is overwhelmingly massive. If you were to gather all the brilliant stars from every one of the thousands of galaxies in the Virgo cluster and place them on a cosmic scale, and then on the other side place this invisible tenuous gas, the gas would win. The intracluster medium contains more mass, more normal matter than all the stars in the cluster combined. It is the true substance of Virgo, and until Chandra it had remained almost entirely hidden from us. This discovery was revolutionary. The space between galaxies was not empty, it was full of a scalding energetic medium that every galaxy in the cluster must move through, like a submarine navigating a dense viscous ocean. This cosmic ocean is not stagnant, it is a repository of history. Within this gas, Chandra's spectrometers can detect the chemical signatures of heavy elements, iron, silicon-oxygen elements forged in the hearts of stars and blasted into space by supernovae. For billions of years, galaxies have been shedding their chemical creations into this medium, enriching it. The ICM is the cluster's collective memory, a chemical record of every star that has ever lived and died within its bounds. Suddenly, the chaotic portraits from Hubble began to make a terrifying new kind of sense. The galaxies were not just being pulled apart by gravity, they were also being assaulted by this invisible superheated hurricane. Imagine a galaxy, a vast but fragile ecosystem of stars, gas and dust falling into the cluster for the first time. For eons it has drifted through the relative emptiness of the cosmic void. But as it crosses the threshold into Virgo's domain, it plunges into this incredibly hot, dense medium. It experiences a ferocious headwind, a cosmic gale blowing at hundreds of kilometers per second. This was a force we had theorized about, but with Chandra, we could finally see its devastating effects written across the cluster. We were witnessing a process of cosmic erosion, a stripping away of the very essence of a galaxy. But to understand precisely what was being stripped away, we needed yet another set of eyes. We needed to see not the hot and the dead, but the cold and the living. For this, we turned our attention back to Earth, to a place that looks more like another planet than our own. High in the Atacama Desert of Chile, on a plateau so arid and thin-aired that life barely clings on, we built our third great explorer, ALMA, the Atacama Large Millimeter Submillimeter Array. It is not a single instrument, but a synchronized fleet of 66 radio dishes, a vast reconfigurable ear pointed at the heavens. ALMA does not see starlight or X-rays. It perceives the faint cold glow of things barely above absolute zero. It is tuned to the whispers of the universe. It detects the cold molecular gas and interstellar dust, the raw frigid ingredients from which new stars are born. If Hubble sees the brilliant cities of stars and Chandra sees the raging fires of the cosmos, ALMA sees the quarries and lumber yards, the fundamental building materials of galactic civilization. When ALMA listened to the galaxies within Virgo, it uncovered the other side of the story Chandra had begun to tell. It targeted those galaxies plunging headfirst into the cluster's core, the ones that Hubble saw as bruised and distorted, and it found that their reservoirs of cold star-forming gas were being systematically and brutally depleted. In galaxies on the outskirts of the cluster, ALMA detected vast dense clouds of molecular hydrogen throbbing with the potential for new creation. But as we looked deeper toward the cluster's center at galaxies that had been residents for longer, the signal grew faint. Their wellsprings of creation were running dry. The gas was missing. By combining the vision of these three great observatories, the full terrifying picture finally emerged. We could at last give the killer a name: ram pressure stripping. It is a process of magnificent, simple violence. As a galaxy ploughs through the hot, dense intracluster medium, that Chandra revealed the headwind it encounters is so powerful that it acts like a celestial sandblaster. It cannot dislodge heavy stars, but the galaxy's most precious and tenuous resource, its vast cold clouds of star-forming gas, is utterly vulnerable. Alma watched as this gas was being forcefully torn away, swept out of the galaxy, and dispersed into the surrounding hot medium. Hubble then provided the stunning visual confirmation. It captured breathtaking images of so-called jellyfish galaxies. These are spiral galaxies caught in the very act of being stripped. Trailing behind them away from their direction of travel are vast, spectacular tendrils of gas and dust glowing with the brilliant blue light of thousands of newborn stars. The intense pressure of the ICM not only strips the gas but also compresses it, triggering a final, desperate burst of star formation within these trailing filaments. It is a beautiful, tragic spectacle, a galaxy giving birth to its last generation of stars in the very material that is being stolen from it. It is the galaxy's funeral pyre blazing brightly before it is extinguished forever. This process explains the strange demographics of the cluster we had puzzled over for so long. The core of Virgo is dominated by red and dead, elliptical and lenticular galaxies, galaxies devoid of gas and with no new stars. Now we know why. They are the survivors, the ancient residents who were stripped of their creative potential billions of years ago. The vibrant blue, star-forming spiral galaxies are found mostly on the outskirts, the newcomers just beginning their perilous plunge. The cluster is a machine for killing galaxies, for systematically shutting down their ability to create and transforming them into sterile stellar fossils. And amidst this grand cosmic struggle, we found a new, even deeper mystery. Hidden in the glare of their larger siblings, our surveys began to reveal an astonishing population of faint ethereal objects, the dwarf galaxies. There are not hundreds, but thousands upon thousands of them peppered throughout the cluster. They are the most common type of galaxy in the universe, yet they are so fragile, so gravitationally tenuous, that they should be the first and easiest victims of ram pressure stripping and tidal disruption. They are the cosmic plankton in an ocean of sharks. Their very existence in such vast numbers, especially near the violent core of the cluster, presents a profound paradox. How do these faint fluffballs of stars survive in an environment that tears apart galaxies 1,000 times their mass? Are they protected by invisible shells of dark matter, far more robust than we predicted? Or are we witnessing a snapshot in time, seeing the last vestiges of a once far greater population doomed to be shredded and dissolved into the intracluster light? These tiny ghost-like galaxies are a quiet testament to a story whose most dramatic chapters are still unwritten. We had set out to map our neighbourhood, and instead we had uncovered a crucible, a relentless engine of change that challenges our most fundamental ideas of what a galaxy is and what it can become. We had discovered that the life of a galaxy is not determined in isolation, but by the ferocity of the cosmic city it calls home. And so to truly understand the forces that bind this celestial empire together, we must turn our gaze from the sprawling diaspora of its member galaxies and focus on the seat of power itself. We have drifted through the elegant arms of spirals and floated past the chaotic swarms of dwarfs, each a story, each a world unto itself. But every great dominion has a capital, a centre of gravity not just in mass but in influence. In the Virgo cluster, that capital has a name spoken with a certain reverence by astronomers Messier 87. From a distance it appears deceptively simple, a soft, featureless smudge of ancient light. There are no brilliant blue arms laced with the fire of new birth, no intricate dust lanes sketching cosmic artwork. M87 is something older, something more primal. It is a supergiant elliptical galaxy, a ghostly, near-perfect sphere of pale yellow light. A city built not of vibrant young stars, but of trillions of aging golden suns. It is less a dynamic metropolis and more a vast silent mausoleum, its residents locked in slow, inexorable orbits around a mystery they can never comprehend. Surrounding this behemoth is a halo of unimaginable scale, a ghostly fog of solitary stars torn from smaller galaxies that strayed too close, their structures unravelled by M87's immense gravitational tide. And within that halo, like a swarm of cosmic fireflies, are its globular clusters. While our own Milky Way might possess a respectable 200 of these ancient dense balls of stars. M87 commands an army of over 12,000. Each one is a fossil, a relic from the universe's infancy, and their sheer number speaks to a history of violent consumption of M87 growing to its colossal size by devouring its neighbours over billions of years. This is not a galaxy. It is a monument to cosmic conquest, the gravitational monarch of the Virgo supercluster, and we are its subjects looking on from our quiet provincial spiral 60 million light-years away. For decades, the sheer mass and quiet dignity of M87 presented a profound puzzle. It sits at the cluster's gravitational heart, the anchor around which so much of the local universe revolves. But what lay within its core, what engine could power such a titan and hold such sway over its environment? The galaxy's serene uniform glow offered no immediate clues. It was a placid ocean of starlight, yet astronomers suspected that beneath that calm surface a monster was sleeping. The first hint that something was profoundly wrong, something violently energetic at the heart of M8A7, came not from what could be seen in the galaxy itself, but from what was being violently ejected from it. As early as 1918, the astronomer Heber Curtis, while studying photographic plates, noted a curious straight ray emerging from the galaxy's core. It was a detail so strange, so out of place against the soft backdrop of the elliptical glow, that it seemed almost an imperfection in the photograph, a scratch on the glass. But it was real, and it was a mystery that would deepen for a century. As our telescopes grew more powerful, this curious ray resolved into one of the most spectacular and terrifying objects in the known universe, a relativistic jet. This was no gentle stream of gas. This was a celestial blowtorch, a focused beam of charged particles, electrons, positrons, blasted out from the galaxy's nucleus and accelerated to over 99% of the speed of light. This luminous spear, glowing with the ghostly blue light of synchrotron radiation, stretches out from M87's heart for over 5,000 light-years. To put that into perspective, if the galaxy's core were in our solar system, the jet would extend far beyond the nearest star, a cosmic searchlight piercing the interstellar void. It is a structure of pure, focused violence. The material within this beam is superheated to millions of degrees, moving so fast that the strange physics of relativity warp its very appearance. We see knots and shockwaves within it, regions where the plasma is compressed and energized, glowing with an intensity that outshines entire star clusters. It is a particle accelerator built on a galactic scale, a testament to an energy source so potent it defies easy comparison. Think of all the energy our own sun will produce over its entire 10 billion year lifetime. The engine powering M87's jet unleashes that amount of energy not over billions of years, but in a matter of minutes. This single unbelievable fact changed everything. The tranquil ancient city of stars was a facade. At its heart lay a furnace of unimaginable power. The jet was the smoking gun, the undeniable evidence of a central engine of creation and destruction. But what could it be? No star, no collection of stars could generate this kind of focused directional power. The answer had to be something far more exotic, something predicted by theory, but for a long time confined to the realm of pure imagination. The answer had to be a black hole. Not just any black hole, not the stellar mass remnants left over from dying stars, but a supermassive black hole, a gravitational singularity of incomprehensible scale. The hypothesis was electrifying. Such an object would be the only thing capable of anchoring a galaxy as vast as M87 and powering a phenomenon as extreme as its jet. The hunt was on not to see the black hole itself, for it is by its very nature invisible, but to see its effects. Astronomers turned their most powerful instruments to the galactic core, peering into the dense, blinding star field at its centre. They weren't looking for a dark spot. They were looking for motion. They were tracking the dance of the stars, the innermost members of that trillion-star city. According to Einstein's theories, stars orbiting a central supermassive object should behave in a very specific way. Close to the object, their orbits should become frantic, their velocities rocketing to incredible speeds, as they are whipped around by its immense gravity. This is precisely what we found. Using the Hubble Space Telescope to gaze deep into M87's heart, astronomers measured the light from its core stars. They saw the telltale signs of extreme gravitational influence. The stars there were moving at hundreds of kilometers per second, a chaotic swarm of suns caught in a gravitational vortex, a celestial maelstrom orbiting a point of utter blackness. The speeds were so high, the orbits so tight that the only object that could be holding them captive was a dark compact mass millions, perhaps billions of times more massive than our Sun, all concentrated into a space smaller than our solar system. The evidence was overwhelming, but it was still indirect. We could see the cage, but we couldn't see the beast inside it. We had measured its shadow, its gravitational footprint on the stars around it, but the ultimate prize remained elusive, a direct image of the abyss itself. To accomplish such a feat would require a telescope not of meters, but of thousands of kilometers in diameter. It would require a telescope the size of the Earth. And so, in one of the most ambitious scientific collaborations in human history, we built one. It was called the Event Horizon Telescope, a global network of radio observatories, from the mountains of Chile to the plains of Spain, from the frozen expanse of Antarctica to the volcanic peaks of Hawaii. All of them synchronized by atomic clocks of impossible precision, swiveling in unison to stare at that single point in the heart of M87. For years they gathered data, not pictures, but petabytes of radio wave information, a torrent of data so vast it couldn't be sent over the internet, but had to be flown on hard drives to central processing facilities. There, supercomputers began the painstaking years-long task of weaving this global symphony of data into a single coherent image. They were attempting to resolve an object so small and so distant it was the equivalent of trying to photograph a single orange on the surface of the moon. The world held its breath. And then in the spring of 2019, the image was revealed. It was a moment that transformed science fiction into scientific fact. There, for all of humanity to see, was the beast. It was not a point of blackness, but something far more profound. It was a ring of fire, a lopsided halo of incandescent plasma, orbiting the very edge of forever. This was the light from superheated gas and dust caught in the black hole's grip, swirling in a final frantic orbit at nearly the speed of light before taking the final plunge. This accretion disk, a maelstrom of matter being torn apart, was glowing so brightly it illuminated the darkness within. And at the centre of that fiery ring was the shadow. It was the abyss, the event horizon. The point of no return made visible against the backdrop of its last meal. We were looking at a wound in the fabric of space-time itself, a direct portrait of gravity bent to its absolute breaking point. The calculations that followed were staggering. The supermassive black hole at the heart of M87, the object we now call M87, contains the mass of 6.5 billion suns. It is a monster beyond all earthly comprehension. If it were placed at the centre of our solar system, its event horizon would swallow the orbits of all the planets stretching out far beyond Neptune. Its gravitational pull is so immense that it warps the very light of the plasma swirling around it, creating the bright, lopsided ring we see in the image. It is the ultimate anchor, the gravitational heart, not just of its galaxy, but of the entire Virgo cluster. And with this image, we finally had the missing piece of the puzzle. We had found the engine. We could now definitively link the monster in the dark to the luminous spear it launches across its galactic kingdom. The connection is one of the most extreme and beautiful processes in all of physics. As gas and dust from interstellar space and torn-apart stars spiral inwards, forming that brilliant accretion disk, not all of it falls past the event horizon. The black hole itself is spinning a gravitational gyroscope of unimaginable mass and energy, dragging the very fabric of space-time around with it. This spinning, combined with the intense magnetic fields embedded within the swirling plasma of the accretion disk, creates a cosmic dynamo. The magnetic field lines anchored in the disk but twisted by the spinning space-time are wound up into tight, colossal funnels extending outwards from the black hole's poles. Within these magnetic funnels, a small fraction of the infalling material, instead of being consumed, is caught. It is captured by these powerful, organised magnetic fields and channeled into two opposing streams. Trapped within this magnetic nozzle, the plasma is accelerated outwards with ferocious power, away from the black hole's gravitational grasp, reaching velocities that are a hair's breadth from the ultimate speed limit of the universe. The supermassive black hole, the Great Devourer, is also a colossal projector. It is both a drain and a fountain. The relativistic jet is its exhaust, the spectacular visible evidence of the messy, violent process of feeding this cosmic leviathan. It is a system of breathtaking power, where the laws of gravity, magnetism, and relativity conspire to create a structure that can influence not just a single star system, or even a single galaxy, but an entire cluster. This is the true significance of M87. Its influence does not stop at the edge of its stellar halo. That 5,000 light-year jet is merely the brightest, most focused part of a much larger, more pervasive phenomenon. As the jet plows through the sparse gas within M87, it eventually loses its tight focus and begins to spread out, inflating enormous invisible bubbles of high-energy particles and magnetic fields into the space beyond the galaxy. We can't see these bubbles with conventional telescopes, but through X-ray and radio observations we can map their ghostly presence. They are colossal structures hundreds of thousands of light-years across, carved out of the hot diffuse gas that permeates the entire Virgo cluster, the intracluster medium. These are the scars of M87's activity, a record of its eruption stretching back millions of years. This process is what astronomers call feedback, and it is the linchpin for understanding how clusters like Virgo evolve. The vast reservoir of hot gas between the galaxies is the raw fuel for star formation. If left to its own devices, this gas would slowly cool, condense, and rain down onto galaxies like M87, triggering massive bursts of new star birth. But this isn't what we observe. For billions of years, the star formation in many of the cluster's largest galaxies has been mysteriously suppressed. The gas is there, but it remains too hot, too puffed up to collapse and form stars. M87's black hole is the reason why. Its jet acts as a cosmic thermostat. Every few million years, as material accretes onto the black hole, the jet fires up, pumping a colossal amount of energy into the surrounding intracluster medium. This injection of energy heats the gas, creating shock waves and turbulence that ripple through the cluster, preventing it from cooling down. M87 is actively regulating its own growth and the growth of its neighbours. It is policing the cluster, ensuring that the era of frantic starbirth is kept in the past. It is sculpting its own environment on a scale of millions of light-years, determining the fate of gas and stars in galaxies that are its distant companions. The sleeping giant is in fact the cluster's restless gatekeeper. The quiet, ancient city of stars is home to an engine that dictates the cosmic weather for its entire neighbourhood, a feedback loop of consumption and eruption that has shaped the Virgo cluster into the structure we see today. We came to M87 seeking the heart of the cluster, and we found it. But it is not a benevolent ruler. It is a cataclysmic engine of physics, a gravitational colossus whose feeding habits have profound consequences for thousands of other galaxies. The awe-inspiring image of its shadow is more than just a picture. It is a key that has unlocked our understanding of the deep symbiotic relationship between the largest galaxies and the supermassive black holes that power them. It has shown us that to comprehend the life of a galaxy, or even a cluster of galaxies, you must first comprehend the monster that lurks in its core. M87 has provided a stunning, visceral answer to how these great cosmic structures are governed. Yet this revelation only deepens the mystery. The intricate dance of feedback we see here is just one of the powerful invisible forces at play. M87 and its black hole may be the most visible architects of the Virgo cluster, but they are not the only ones. For there is another far more pervasive influence at work, a substance we cannot see, cannot touch, and cannot yet understand, but whose gravitational presence dominates this entire region of space. The story of Virgo is not just a story of light, but also one of profound, overwhelming darkness. But the fury emanating from Messier 87, that celestial titan we've just witnessed, is not confined to its spectacular galaxy-spanning jets. That visible violence is merely the loudest expression of a far more pervasive, far more insidious force at work throughout the Virgo cluster. For every galaxy caught in the direct path of that cosmic blowtorch, 1,000 more are suffering a slower, quieter, but equally dramatic fate. They are travellers on a dark path, a one-way road into the heart of this gravitational storm, from which there is no escape and no return to what they once were. To understand their journey is to witness the slow, inexorable dismantling of a galaxy piece by piece until nothing remains but a pale, silent ghost. Imagine a vibrant spiral galaxy, much like our own Milky Way on the cosmic frontier. For billions of years it has drifted through the tranquil emptiness of the intergalactic void, a self-contained island universe brimming with potential. Its graceful arms, traced by the brilliant blue light of newborn stars, are vast, cold reservoirs of hydrogen gas, the raw fuel for creation. It is a place of endless stellar birth, a dynamic living system. But its long, peaceful journey is ending. It has reached the gravitational edge of the Virgo cluster, and it is beginning to fall inward. At first, the change is subtle. The pull is gentle, a cosmic tide drawing it closer to the cluster's dense core. The galaxy accelerates, picking up speed as it plummets toward the metropolis of worlds at Virgo's center. Then it hits the wall. Not a physical wall, but something far more powerful, the intracluster medium. This is the space between the galaxies, but here in Virgo it is not empty. It's a vast unseen ocean of gas heated to millions of degrees by the combined gravity and energy output of 1,000 galaxies. As our unsuspecting spiral plunges into this superheated plasma at over 1 million miles per hour, it experiences a force of unimaginable power. A ferocious headwind of searing gas slams into it, a process astronomers call ram pressure stripping. It is a cosmic sandblasting on a scale that defies imagination. The galaxy's own tenuous halo of gas, its protective outer atmosphere, is the first to be torn away, shredded into incandescent filaments that trail behind it like smoke in a gale. We can see this violent process unfolding in real time across the chasm of 60 million light-years. Telescopes reveal hauntingly beautiful and deeply unsettling images of what are nicknamed jellyfish galaxies. They are spirals caught in the act of being destroyed, their once majestic arms now distorted, and bleeding long, luminous tentacles of gas and newborn stars into the void. These tendrils, sometimes stretching for hundreds of thousands of light-years, are the galaxy's lifeblood being ripped from its body. Within these stolen streams, the stripped gas is compressed, triggering one last brilliant and desperate burst of star formation, a final, fleeting fireworks display before the darkness sets in. It is a beautiful death, a swan song written in the language of exploding stars, but it is a death nonetheless. For the galaxy itself, the consequences are terminal. Without its vast reserves of cold gas, the engine of creation sputters and dies. The stellar nurseries in its spiral arms, once churning out millions of suns, fall silent. No new blue stars, massive and bright, will ignite. The galaxy is being starved. Over hundreds of millions of years, a cosmic eye blink, it undergoes a profound transformation. The brilliant blue and vibrant pink of active starbirth fade away, replaced by the uniform, sickly yellow-orange glow of an aging, dying stellar population. The elegant spiral arms, no longer defined by glowing gas clouds and young star clusters, dissolve and retract. The galaxy's very shape begins to morph, its disk, thickening its structure, rounding out until it becomes a featureless, bloated entity known as a lenticular or anemic spiral galaxy. It is now a shadow of its former self, a relic of a more dynamic past. It still contains billions of stars, but they are old stars marching in lockstep toward their own quiet ends. The galaxy has been robbed of its future, its potential for renewal extinguished forever. This is the fate that awaits the majority of galaxies that call the Virgo cluster home. When we look toward the cluster's core, we don't see a vibrant collection of spirals like those in the cosmic hinterlands. We see a graveyard. The center is dominated by these red, dead and massive elliptical and lenticular galaxies, cosmic fossils that bear the scars of their violent journey through the cluster's heart. They are the end state, the final chapter in the story of galactic evolution. Within this extreme environment, each one a testament to the immense power of the cluster itself. They have survived their fall, but at the cost of their vitality. Yet as we trace these galactic tragedies and map the forces responsible, a far deeper and more unsettling mystery emerges. The visible destruction, the ram pressure stripping, the gravitational tides, all of these are driven by the intracluster medium and the collective gravity of the galaxies we can see. But when we add it all up, the numbers simply don't work. The equation is broken. The galaxies within Virgo are moving with astonishing velocities, zipping around the cluster's center of mass, like frantic bees around a hive. Their speeds are so immense that the gravitational pull of all the stars, all the gas and all the dust we can detect is woefully insufficient to keep the cluster from flying apart. If what we see is all there is, the Virgo cluster should have disintegrated billions of years ago, its member galaxies flung out into the void like stones from a broken sling. But it hasn't. It is here. It is ancient. It is gravitationally bound. This profound contradiction forces us to confront an astonishing and deeply humbling reality. The vast majority of the Virgo cluster is completely invisible to us. The stars and galaxies, the glowing gas M87's ferocious jets, all of this, the sum total of everything we can see, accounts for less than 15% of the cluster's total mass. The rest, a staggering 85%, is something else entirely. Something that emits no light, reflects no radiation, and interacts with our universe through only one fundamental force, gravity. We call it dark matter. It is the ghost in the machine, the invisible scaffolding upon which our entire cosmic neighbourhood is built. It is the true master of the Virgo cluster. This isn't just a theory or a convenient fudge factor to make our models work. We can map its presence. We can see its shadow. As light from far more distant galaxies billions of light years behind Virgo travels toward us, its path is warped and bent by the immense gravitational field of the cluster. This is gravitational lensing, a prediction of Einstein's theory of general relativity, and it allows us to use the Virgo cluster as a colossal cosmic magnifying glass. The patterns of distortion, the subtle arcs and sheared shapes of those background galaxies reveal the precise distribution of mass within the cluster. And what they show us is a vast, roughly spherical halo of invisible matter engulfing the entire system, extending far beyond the outermost visible galaxies. This invisible ocean of dark matter is what holds Virgo together. It is the source of the immense gravitational potential that accelerates galaxies to incredible speeds. It is the anchor that prevents them from escaping. The hot intracluster gas, the very medium that strips galaxies of their future, is itself trapped and superheated within this dark matter basin. The galaxies we see are like luminous corks bobbing on an unseen powerful current, their paths dictated not by each other, but by the contours of this invisible gravitational landscape. M87 sits at the very bottom of this gravitational well, the deepest point in the dark matter halo, which is why it grew so massive and why it commands such influence over its surroundings. It is the king, but dark matter is the throne it sits upon. The revelation of this dark scaffolding solves one mystery only to create a multitude of others, complicating our quest to understand Virgo on a fundamental level. For if we cannot see the primary source of gravity, how can we possibly hope to chart the intricate dance of the galaxies within it? Our attempts to create a true three-dimensional map of this celestial metropolis are fraught with profound challenges, turning what seems like a simple observational task into a maddeningly complex cosmic puzzle. The cluster is not a flat photograph projected onto the sky. It is a sprawling dynamic volume of space with immense depth, and our position on the outside looking in creates a host of bewildering illusions. Our primary tool for measuring cosmic distances and velocities is redshift, the stretching of a galaxy's light toward the red end of the spectrum as it moves away from us. The greater the redshift, the faster it's receding, and due to the expansion of the universe, the farther away it is. But inside a massive gravitationally bound structure, like the Virgo cluster, this simple relationship breaks down completely. A galaxy's redshift is no longer a pure measure of cosmic distance. It's now a contaminated signal, a combination of the overall cosmic expansion and the galaxy's own peculiar velocity as it orbits within the cluster's gravitational well. A galaxy on the far side of the cluster falling inward toward us will have its cosmic redshift partially cancelled out, making it appear artificially close. Conversely, a galaxy on the near side of the cluster, moving away from us as it orbits, will have its velocity added to the cosmic expansion, making it appear artificially distant. This effect creates a bizarre and frustrating optical illusion known to astronomers as the finger of God. When we plot the positions of Virgo's galaxies based on their redshifts, we don't see a spherical cluster. Instead, we see a grotesquely elongated structure pointing directly at us, as if a cosmic finger is jabbing out from the heavens. This is not the true shape of the cluster. It is a distortion, an artifact of our inability to disentangle a galaxy's internal motion from its distance. We are trying to survey a chaotic swarm of bees from a single vantage point where every bee's movement toward or away from us corrupts our measurement of its depth. Is that galaxy truly at the heart of the cluster, or is it a foreground object just beginning its fall? Is that distant-looking galaxy genuinely on the far edge, or is it much closer but racing away from us on its orbital path? Untangling this knot is one of the greatest challenges in modern observational cosmology. It requires painstakingly measuring distances through other more difficult methods, like tracking the brightness of specific types of stars or supernovae, a process that can only be done for a fraction of the cluster's members. For the rest, we're left with a fundamental uncertainty, a statistical fog that clouds our view of Virgo's true architecture. This fog permeates every subsequent calculation we try to make. Our estimates of the cluster's total mass, the precise distribution of its dark matter, the orbital histories of its galaxies and the timeline of their transformation. All of it is built upon a foundation that is inherently shaky. We are trying to understand the physics of a gravitational storm while being unable to confidently map the positions of the clouds within it. Every new survey, every deeper image adds more galaxies to our catalogue, but also adds more complexity to the puzzle. We are confronted with the humbling truth that our galactic neighbourhood, the most significant structure in our corner of the universe, remains a place of profound ambiguity. We see the brutal aftermath of its environmental forces, the skeletal remains of galaxies stripped of their vitality. We have felt the undeniable gravitational grip of its vast, invisible dark matter halo. Yet the complete picture, the full gravitational tapestry that weaves these elements together remains tantalizingly out of reach. We are like cartographers from a bygone era trying to map a new continent from a single distant shoreline, aware of its immense scale, but unable to penetrate the mist that shroud its interior. To do that, to finally chart this wilderness, we will need more than just bigger telescopes. We will need entirely new ways of seeing, and so we stand at a precipice of understanding. All the pieces are now on the table. The ghostly X-ray light of the intracluster medium, a searingly hot ocean of plasma binding the cluster together. The faint, tragic trails of hydrogen gas torn like ribbons from galaxies plunging into the abyss. The strange, anemic forms of lenticulars and ellipticals, cosmic elders clustered near the core, their star-forming days long behind them. Each observation, each photon captured from 54 million light-years away has been a clue, a breadcrumb on the trail of a grand cosmic mystery. For too long, we saw the Virgo cluster as a static portrait of galaxies, a beautiful but silent collection. But now, with the full weight of our evidence assembled, the silence breaks. We can finally hear the symphony of its violence, the hum of its creation, and the whispers of its destiny and our own. This is no longer a portrait. It is a living, breathing, evolving creature. And now at last we can begin to dissect its anatomy to understand the forces that give it life and that bring about death on a scale that defies imagination. The time for gathering clues is over. The time for a verdict has arrived. The central question, the one that has haunted astronomers for generations, concerns the profound transformation of galaxies. Why are the bustling star-filled spirals like our own Milky Way so rare in Virgo's core? Where did their brilliant blue arms and glittering nebulae go? The answer is not a single event, but a relentless multi-pronged assault, a trial by fire, wind, and gravity. Imagine a vibrant spiral galaxy, a pinwheel of youthful stars and cool gas on the outskirts of the cluster. For billions of years, it has lived in relative isolation, a self-contained island universe. But it feels a pull, a persistent gentle summons from a source of gravity so immense it warps the fabric of space-time itself. This is Virgo's siren song. As the galaxy answers the call, accelerating towards the cluster's center, it crosses an invisible boundary. It plunges into that superheated ocean of intracluster gas we detected with our X-ray eyes. Suddenly, this galaxy is no longer moving through a near-perfect vacuum. It is fighting against a cosmic headwind, a gale of plasma heated to millions of degrees, blowing at thousands of kilometers per second. This is ram pressure stripping, and it is perhaps the most brutal act of galactic transformation. the wind of plasma is utterly relentless. It cares nothing for the galaxy's own gravity. It slams into the galaxy's vast, delicate reservoirs of cool hydrogen, the fuel for future generations of stars. At first, the gas on the leading edge is shocked, compressed, and then violently stripped away, peeling back from the galactic disk like paint from a sandblasted wall. We have seen the evidence directly in the long ethereal tails of atomic hydrogen trailing behind galaxies like NGC 4B569. This is not just gas. It is a galaxy's lifeblood, its potential, its future being spilled out into the void. Star formation, once a vibrant engine of creation, sputters and dies, starved of fuel. The beautiful spiral arms, no longer illuminated by the brilliant short-lived blue stars, begin to fade. The galaxy is being hollowed out from the inside, its fiery soul, extinguished by an invisible force. It is a process of cosmic exsanguination, leaving behind a pale, anemic ghost of its former self. A red and dead elliptical, or a featureless lenticular galaxy, is born not from a gentle evolution, but from this swift, violent metamorphosis. Its journey into the heart of Virgo is a one-way trip to senescence. But ram pressure stripping is not the only weapon in Virgo's arsenal. For smaller galaxies, the cluster deploys a more intimate form of violence. As a dwarf galaxy orbits a giant like Messier 87, it experiences rapid, repeated gravitational tugs. Each close pass acts like a tidal shock, a gravitational slap that stirs up its internal structure and flings its outermost stars into the void. This is galactic harassment, a death by 1,000 cuts. Over millions of years, the dwarf is gradually dismembered, its stellar body dissolving into faint streams that weave themselves into the diffuse halo of its massive tormentor. We see these stellar wraiths, these ghostly remnants of devoured galaxies haunting the space between Virgo's giants, a testament to the cluster's cannibalistic nature. And for those galaxies that manage to survive their initial plunge, a slower, more insidious process takes hold: strangulation. Once a galaxy is deep within the cluster, its vast tenuous halo of hot gas, its own atmospheric shield and secondary fuel reserve is stripped away by the collective gravity of the cluster. Without this protective halo, the galaxy can no longer draw in fresh gas from the cosmic web. It is cut off from its lifeline, isolated, and left to slowly consume its remaining fuel. Star formation doesn't end with a bang, but with a long drawn-out whimper. The galaxy is slowly strangled over cosmic time, its lights dimming one by one, until only the old red, long-lived stars remain. This trinity of transformation, the swift violence of ram pressure, the grinding torment of harassment, and the slow suffocation of strangulation, solves the great mystery of Virgo's galactic population. The cluster is not merely a collection of galaxies. It is a vast, efficient processing plant. It draws in pristine, gas-rich spirals from the cosmic wilderness, subjects them to these incredible environmental pressures, and transforms them into the quiescent passive galaxies that dominate its core. Virgo is a crucible forging the evolution of galaxies on an industrial scale. And watching this process unfold 54 million light-years away is like watching a film of our own galaxy's potential future. The beauty of Virgo's structure is, in truth, a monument built upon the skeletal remains of countless galaxies that came before. But the visible matter, the galaxies and the hot gas, is only the stage. The true director of this entire cosmic drama has remained hidden, an unseen puppet master, conducting the symphony of gravity from the shadows. To truly understand Virgo, we must confront the ghost in the machine: dark matter. Everything we see, every star, every galaxy, every wisp of gas is moving far too fast. The galaxies within Virgo are careening through space at such tremendous velocities that the cluster should have flown apart billions of years ago. The gravity of all the visible matter combined is simply not enough to hold it together. It's like watching a carousel spin at the speed of a jet engine. The horses should be flung off into the distance, yet they are not. The Virgo cluster remains bound, a coherent, majestic structure. The solution to this paradox is as profound as it is invisible. Virgo, and indeed the entire universe, is dominated by a substance we cannot see, cannot touch, and cannot directly detect. This dark matter, 5 times more abundant than all the normal matter that makes up you, me and the stars, provides the missing mass. It is the gravitational glue, the cosmic anchor holding this magnificent assembly of galaxies in its grasp. Its presence is revealed not by light, but by its unyielding influence on everything that does shine. We map its distribution by watching how its immense gravity bends and distorts the light from far more distant objects, a phenomenon known as gravitational lensing. The light from a background quasar travelling for billions of years passes through Virgo, and its path is warped by the invisible mountains and valleys of dark matter, creating multiple distorted images of the same object. By analysing this distortion, we can create a map of the unseen, and what a map it reveals. The dark matter in Virgo is not a uniform cloud. It forms a vast, intricate scaffold, a cosmic web of filaments and clumps. The most massive galaxies like Messier 87 sit at the bottom of the deepest gravitational wells nestled within the densest concentrations of this mysterious substance. These are the nodes of the web, the junctions where the cosmic highways of dark matter converge. The galaxies themselves are like luminous corks bobbing on a dark invisible ocean, their motions tracing the currents and eddies of its gravitational flow. Dark matter is not just a passive glue, it is the architect. It was the gravitational blueprint laid down in the very early universe that guided the flow of primordial gas and dictated where galaxies would form. It was the dark matter filaments that acted as cosmic rivers, channeling matter across millions of light years to feed the growing appetite of the nascent Virgo cluster. So when we see a spiral galaxy plunging into the cluster core, we are not just seeing a random event. We are witnessing the final chapter of a journey that began billions of years ago, a journey along a preordained path carved out by an invisible substance. Understanding the precise shape and structure of Virgo's dark matter halo is therefore not just an academic exercise. It is fundamental to understanding the very skeleton upon which the large-scale structure of our universe is built. And yet this grand invisible architecture is not the only unseen force at play. Deep within the hearts of Virgo's most massive galaxies lie engines of such ferocious power they can rival the light of the entire cluster, the supermassive black holes. For decades we viewed these objects as cosmic curiosities, passive gravitational drains at the centre of galaxies, but our view has been revolutionised in no small part by the monstrous black hole at the heart of Messier 87. This behemoth, over 6.5 billion times the mass of our Sun, is not a quiet giant. It is an active cosmic engine. As gas and stars are drawn towards its event horizon, they form a swirling accretion disk, a vortex of matter, heated to unimaginable temperatures brighter than 1 trillion stars. But not all of this matter falls in. A significant fraction is channeled by intense magnetic fields and ejected outwards in 2 colossal jets of relativistic particles, travelling at nearly the speed of light. We have seen these jets. They are celestial blowtorches punching out of M87's core and extending for thousands of light years into the intracluster medium. This is the phenomenon of active galactic nucleus or AGN feedback, and its impact is profound. These jets are so energetic that they pump enormous amounts of heat and momentum into the surrounding gas. They carve out vast cavities in the hot plasma of the cluster, preventing it from cooling, collapsing and forming new stars. M87's black hole is acting as a cosmic thermostat. It is single-handedly regulating the environment of the entire cluster core. This discovery fundamentally changes our understanding of galactic evolution. It means the transformation of a galaxy is not just dictated by external forces like ram pressure stripping. It is also governed by an internal engine. A galaxy's fate is intertwined with the behaviour of the monster at its heart. The black hole's feeding cycle, periods of intense activity followed by quiescence, can determine whether a galaxy lives a long life of star formation or is prematurely sterilised. The jets from M87 are a sterilising agent, ensuring that the gas in its vicinity remains too hot and diffuse to ever create a new generation of stars. This explains in part why the cores of rich clusters are so devoid of star formation. The most massive galaxies powered by the most massive black holes actively police their environment, shutting down creation on a cluster-wide scale. The supermassive black hole is not merely a feature of a galaxy. It is a co-pilot of its evolution, a force of nature that shapes not only its own host but the entire cosmic neighbourhood. It is the final piece of the puzzle, the link between the smallest scales of accretion disks and the larger scales of cluster dynamics. With this synthesis of environmental processes, the guiding hand of dark matter, and the regulatory power of black holes, the portrait of Virgo is finally complete. But how can we be certain that this complex, violent and beautiful story is the right one? The answer lies not in the sky, but inside our most powerful supercomputers. The Virgo cluster in its magnificent complexity serves as the ultimate benchmark for our understanding of the cosmos, a final exam for our theories of universe formation. Scientists can now create digital twins of the universe. They begin with a virtual box of dark matter and hydrogen gas governed by the known laws of physics, gravity, fluid dynamics, thermodynamics, and set the initial conditions to match those of the early universe just after the Big Bang. Then they press play. What unfolds over billions of years of simulated time is nothing short of breathtaking. The dark matter collapses under its own gravity, forming the delicate filaments of the cosmic web. Gas is drawn into these filaments, cools, and begins to form the first stars and galaxies. These galaxies merge and grow, orbiting and interacting within the gravitational framework of the dark matter halos. It is a virtual universe born from pure code and physical law. The ultimate test is this: out of these simulations, does a structure that looks and behaves like the Virgo cluster naturally emerge? Does the simulation correctly predict the number of spirals versus ellipticals? Does it reproduce the hot X-ray emitting gas of the intracluster medium? Does it show galaxies having their gas stripped away as they fall into the core? For years the simulation struggled. They would produce clusters that were too dense or galaxies that were too massive. Something was missing. The breakthrough came when the models became sophisticated enough to include the physics of supernova explosions, and crucially the feedback from supermassive black holes. When the simulations included the energy pumped out by these cosmic engines, which pushes gas out of galaxies and heats the cluster medium, everything clicked into place. Suddenly, the digital universe began to look uncannily like the real one. The simulations for the first time began to birth virtual Virgo clusters that were statistically indistinguishable from the real thing. This was a moment of profound triumph. It was confirmation that our grand synthesis, this intricate dance of gravity, dark matter, gas dynamics, and black hole feedback, was not just a compelling story, but a scientifically robust model of reality. The Virgo cluster is our cosmological ground truth. By holding a mirror up to our simulations, it allows us to test, refine, and validate our entire picture of how the universe builds its most majestic structures. It gives us the confidence to look at the cosmos and say, with a degree of certainty that would have been unimaginable a century ago, we understand how this works. And with that understanding comes a chilling, exhilarating realization. The story of Virgo is not just the story of a distant collection of galaxies. It is a direct preview of our own future, our local group. A modest collection of galaxies, including our Milky Way and our larger neighbour Andromeda, is not an island. We're on the outskirts of Virgo's vast gravitational empire. Every measurement of our motion through the cosmos shows one unmistakable fact: we are falling towards it. We are part of what is known as the Virgo supercluster, and the Virgo cluster is its dense gravitational heart. Our summons has been issued. Our journey has already begun. At our current speed of several hundred kilometers per second, the journey will take many billions of years, but the outcome is as certain as gravity itself. Before we ever reach the cluster's edge, our own local group will have undergone its own violent transformation, as the Milky Way and Andromeda are destined to collide and merge in about 4.5 billion years, forming a single giant elliptical galaxy, Milkomeda. Our distant descendants, should they exist, may look up at a sky utterly alien to our own. But that great merger will only be the prelude. For the newly forged Milkomeda will continue its inexorable plunge, a single massive galaxy, drawn into the galactic maelstrom ahead. It will cross that same invisible boundary, feel that same cosmic headwind, and face that same trial by fire that countless galaxies have faced before it. Our galactic home is on a collision course with destiny. The dynamic, violent, and transformative laboratory of the Virgo cluster is not just something we observe from a safe distance. It is our final destination. And so, our long gaze across 65 million light-years of cosmic history begins its return, forever changed by what it has witnessed. The light from Virgo that graces our telescopes tonight began its journey when dinosaurs still roamed the Earth, a final faint echo of their reign. That ancient light has travelled through an expanding universe, across the desolate gulf of intergalactic space, to arrive here now carrying with it a story of unparalleled grandeur. In this sprawling celestial metropolis, this gravitational nexus of thousands of galaxies, we have found more than just a beautiful collection of stars. We have uncovered a living laboratory for the cosmos itself. It is a place where the universe puts its most fundamental processes on display, a dynamic stage, where we can watch the grand narrative of cosmic evolution unfold in real time. For generations, we looked upon those faint ethereal smudges in our eyepieces with a sense of profound mystery, cataloguing them as mere curiosities. Now we see them for what they truly are, the building blocks of everything, the crucibles of creation and destruction, each a chapter in a colossal story written in gravity and light. Our journey through this cluster has been a revelation, a peeling back of cosmic layers to reveal the intricate machinery beneath. We have walked among the giants, the regal, elliptical galaxies like Messier 87, whose placid golden exteriors conceal hearts of unimaginable violence, and whose gravitational reach dictates the fate of their lesser neighbours. In their serene glow, we have read the history of countless galactic mergers, a story of cosmic cannibalism on a scale that defies comprehension, leaving behind these bloated, star-rich relics. We have also soared alongside the graceful spirals galaxies, much like our own Milky Way, witnessing their harrowing rite of passage as they plunge into the cluster's depths. We watch through the unblinking eyes of our observatories as they are relentlessly harassed by the superheated intra-cluster medium, their delicate arms of gas and dust stripped away in fiery trails of ram pressure, their star-forming nurseries extinguished in a slow, inexorable cosmic strangulation. Virgo has shown us with brutal clarity that a galaxy's destiny is not solely its own. It is profoundly shaped and ultimately decided by its environment. It is the ultimate lesson in nature versus nurture played out on a galactic canvas. Beyond the visible, we learn to see the invisible, to perceive the true architecture of this immense structure. By tracing the subtle, patient bending of starlight from far more distant sources, we mapped the unseen. We found the ghost in the machine, the colossal overarching halo of dark matter that is Virgo's true foundation. This mysterious non-luminous substance, this gravitational scaffolding of the universe, reveals its presence not by what it emits, but by the sheer undeniable force of its gravity. It is the invisible skeleton upon which the galaxies, the shining jewels of the cosmos, are merely draped. In the Virgo cluster, this dark matter is not a uniform shroud, but a complex, lumpy and filamentary web, a tapestry of immense density that dictates the cosmic choreography of every star, every planet, and every cloud of gas within its grasp. Understanding its distribution here in our own cosmic backyard is not an academic exercise. It is the key to unlocking one of the most profound mysteries in all of science, a substance that outweighs all the matter we can see by a factor of 5, yet whose fundamental nature remains a complete and tantalizing enigma. Virgo serves as our primary testing ground, a place where our theories about this cosmic ghost are put to the ultimate test against observational reality. The cluster has also become our Rosetta Stone for understanding the very forces that govern existence. Here the titanic struggle between the outward push of dark energy, driving the universe's accelerated expansion, and the relentless inward pull of gravity is laid bare. Within the supercluster, gravity is still king. The inexorable attraction between these thousands of galaxies has overcome the cosmic expansion, binding them together in a shared destiny. Virgo is a testament to gravity's enduring power, its ability to gather matter over unimaginable scales to build structures of breathtaking complexity from the primordial soup of the Big Bang. From the gentle dance of binary stars to the furious accretion of matter onto a supermassive black hole, every gravitational process is amplified and exhibited here. We see the past in the ancient globular clusters orbiting M87, the present in the dynamic interactions between infalling galaxies, and the future in the slow gravitational settling that will one day merge many of these galaxies into an even greater cosmic titan. It is a story of structure formation, the fundamental process by which an almost uniform early universe gave rise to the magnificent complexity we see today. Yet for all that we have learned, for every layer we have peeled back, our journey has primarily served to reveal the vastness of our own ignorance. The view from this summit of knowledge only reveals a higher, more daunting peak shrouded in mist. Each answer has unlocked a dozen more profound and challenging questions that push the very limits of our technology and our imagination. We see the effects of ram pressure stripping, but what are the precise fluid dynamics that govern this process on kiloparsec scales? How does the turbulence and magnetic chaos within the intracluster medium influence the fate of a galaxy's magnetic field as it passes through? We have mapped the great halo of dark matter, but is it smooth, or is it populated by millions of smaller Earth mass subhalos? As some theories predict, finding these gravitational motes would be a revolutionary confirmation of our cold dark matter paradigm. And what of the intracluster light, that ghostly ethereal glow of trillions of orphaned stars flung from their homes during ancient galactic collisions? What can these lonely wanderers tell us about the violent history of their parent galaxies and the hierarchical growth of the cluster itself? The mysteries deepen the closer we look. What is the ultimate origin of the ultra-compact dwarf galaxies we find sprinkled throughout Virgo's core? Are they the stripped-down nuclei of tidally shredded galaxies, or are they a fundamentally new class of object born dense and small? How does the monstrous jet erupting from Messier 87's core truly regulate the temperature of the surrounding gas, acting as a cosmic thermostat that prevents runaway star formation in the cluster's heart? The feedback loop between a supermassive black hole and its host environment is one of the most critical yet poorly understood processes in astrophysics, and Virgo provides our most spectacular and accessible example. And then there is the puzzle of the so-called missing baryons, the ordinary matter that our cosmological models predict should be present in the cluster, but that we cannot seem to find in stars or hot gas. Where is it hiding? Is it locked away in a warm, hot intergalactic medium, a diffuse, tenuous fog that is fiendishly difficult to detect? These are not trivial questions. Answering them is essential to completing our cosmic inventory, to truly understanding the composition and evolution of the universe we inhabit. The Virgo cluster, having answered so much now, stands before us as the guardian of these deeper secrets, challenging us to look again, but this time with new eyes. And those new eyes are coming. Humanity is on the cusp of a new golden age of astronomy, preparing to launch a new generation of sentinels into the heavens. Observatories of such power and sophistication, they will make our current achievements seem like a preamble. First among them is the James Webb Space Telescope, our infrared oracle in the void. Drifting silently 1,000,000 miles from Earth, its great golden mirror shielded from the sun's glare, Webb is designed to see the universe in wavelengths invisible to the human eye. It will peer through the veils of dust that shroud the birth of stars within Virgo's galaxies, revealing the intricate processes of stellar creation with breathtaking clarity. More profoundly, Webb is a time machine. It will capture the faint red-shifted light of the cluster's most ancient components, perhaps even spotting the protogalaxies that were the very first seeds of this immense structure, seeing them not as they are now, but as they were over 12 billion years ago. It will analyse the chemical composition of individual star clusters, searching for the first heavy elements forged in the hearts of primordial stars, and perhaps even study the atmospheres of the countless rogue planets we believe to drift cold and alone in the intergalactic dark. For Webb, Virgo is not just a target, it is a treasure chest of cosmic fossils waiting to be unearthed. On the ground, another revolution is brewing. High in the Chilean Andes, the Vera C. Rubin Observatory is preparing to undertake a survey of unprecedented scale, the Legacy Survey of Space and Time. This facility is not designed to stare deeply at one patch of sky, but to scan the entire visible southern sky every few nights, over and over for a decade. It is a cosmic cinematographer poised to create not a static portrait of the Virgo cluster, but a full-length feature film. It will map the cluster's structure in 3 dimensions with unparalleled precision by observing the subtle gravitational lensing of millions of background galaxies, but its true power lies in the domain of time. Rubin will catch the universe in the act. It will discover thousands of supernovae exploding within Virgo's galaxies, using these standard candles to refine our measurements of the universe's expansion. It will detect the flicker of variable stars, the death cries of stars torn apart by black holes, and the faint moving glints of asteroids and comets within our own solar system, photobombing the deep field images. By monitoring the cluster relentlessly, the Rubin Observatory will reveal its dynamic living nature. It will track the orbits of dwarf galaxies, witness tidal streams being ripped into the intra-cluster void, and discover entirely new phenomena that we cannot yet even imagine. The sheer volume of data it will produce, a torrent of information unlike anything astronomers have ever handled, will require new forms of artificial intelligence just to sift through, guaranteeing that its greatest discoveries may well be the ones we never expected, and they will not be alone. A fleet of future observatories will join this grand quest, each designed to see the cluster in a different light, adding another layer to our understanding. Future X-ray telescopes like the proposed Athena Observatory will map the hot intracluster medium with such exquisite detail that we will be able to trace the shock waves and turbulence created by infalling galaxies, essentially taking the temperature of Virgo's cosmic weather systems. On the radio front, the square-kilometre array, a continent-spanning network of dishes, will chart the vast invisible architecture of magnetic fields that thread through the cluster, a cosmic web of magnetism that shapes the flow of gas and high-energy particles. Each new instrument, each new wavelength will provide a new piece of the puzzle. By combining their vision, we will move from a two-dimensional photograph to a fully immersive, multi-sensory holographic model of our galactic neighbourhood. We will see the hot gas of the X-rays, the old stars of the visible light, the newborn stars of the infrared, and the magnetic skeleton of the radio waves, all woven together with the invisible gravity of dark matter. This is the future of our exploration, a complete holistic understanding of a cosmic ecosystem, from its largest structures down to its smallest, most ephemeral events. As our voyage of discovery concludes, we are left with one final humbling realization. Our relationship with the Virgo cluster is not merely that of a distant, detached observer. We are inextricably part of its story. The Milky Way, our beautiful serene home, is not an island universe in splendid isolation. We reside on the far-flung outskirts of this great supercluster, and for billions of years we have felt its pull. Our galaxy, along with Andromeda and the other members of our local group, is being drawn toward it. We are falling. This is not a cataclysmic imminent collision, but a slow, majestic gravitational infall, a cosmic pilgrimage that will take longer than the current age of the Earth. We are moving towards the Great Attractor, the centre of mass of our local universe, a region dominated by the immense gravity of the Virgo cluster and its neighbouring assemblies. Our ultimate destiny, billions of years from now, is to merge with this cosmic continent. The descendants of our galaxy, whatever form they may take, will one day become citizens of the great metropolis. Their night sky ablaze with the light of thousands of neighbouring galaxies, no longer distant smudges but brilliant sprawling islands of stars. This journey, this inexorable pull towards the heart of Virgo, is a profound reminder of our place in the cosmos. We are not separate from the universe. We are a product of its laws and a participant in its ongoing evolution. The same force of gravity that holds you to your chair is orchestrating this celestial dance on a scale of 100 million light-years. The story of the Virgo cluster is therefore not just the story of them of distant galaxies far, far away. It is in the grandest sense our story. It is our past showing us the processes of assembly and growth from which galaxies like our own emerged. It is our present providing the cosmic context, the gravitational landscape that defines our place in the universe. And it is our very, very distant future, a glimpse of the ultimate fate that awaits our galactic home. We look out at this magnificent tapestry of light and gravity, and we see the universe in all its terrifying beauty, its creative and destructive power, its endless capacity for complexity and change. The story is not over. The light from Virgo continues to fall upon us, carrying new secrets and new challenges. And we in turn continue to look up, driven by an unquenchable curiosity, forever reaching for the light, forever part of the ever-unfolding story of the cosmos.